Hello guys, welcome to High School Physics, Digital Electronics today. Okay, won't take long and it's not as scary as it sounds. We're going to look at analog and digital signals. We're going to look at gates, which are just a type of switch. Okay, and then truth tables. That's it. Okay, now it's a lovely bit of physics to get your head around. Okay, and once you've nailed it, it's just going to stay with you and you're going to do really well in the exam. Okay. Let's dive into this and see what we can do. So analog and digital signals, here we go. All right. Now, analog, you've heard of AC. Okay. AC is a wave which just varies all the time. Okay. AC can be like a sine wave like this. Okay. That's an analog signal. That's it. It just varies, okay? It varies, it needn't be down there. It could just be like this, okay? It's just a signal which varies all the values between 0 and the maximum, just all of them, just like that. That's it, analog, okay? Digital is just discrete values of voltage. It's usually a high voltage or a low voltage, and a high voltage and a low voltage. Okay. The way I would think about it is this, guys. I think about it like in terms of people. I know it sounds a bit strange, right? But if you can't quite think about it like this. Okay. An analog person, you might know an analog person who, when they get angry, they get a little bit angry, and then they get a bit more angry, and then you know that if you just push them a bit more, they're really going to go. Yeah, and you may get a bit of fun out of teasing that person or just pushing them along a bit. Yeah, that's like an analog person, isn't it? You know, you can just wind them up, okay, and you'll know where to stop. Yeah, you might have your favorite uncle. You might just give a little bit of light. You know where to stop, right? And a digital person is like, whoa, they just go, they just go off the deep end. There's no warning. They're just like really nice, or wow, they've kind of like left the planet. And that's the way you can get your head around it, maybe. I don't know. Okay, but use whatever analogy you want, guys. Okay, let's go back to this. So let's go back to our analog and digital signals. Okay, analog just varies. Yeah, just like volume, you know, it gets louder and softer and all the little values in between. And digital voltage, highs and lows. Okay, and then what we do with digital, because we're doing physics, guys, and we're quintessentially lazy, yeah, because we like to use formula, yeah. With digital, we just go, well, you know, when it's a high, it's a 1 value, and when it's low, it's a 0. And that's it. That's what we do. We just use those values. You look on the switches of lots of things. Go and do the vacuum cleaning tonight, okay? Dig out the vacuum cleaner. And when you look at the vacuum cleaner, you look at the switch, and not on the vacuum cleaner, on lots of things. The on-off switch looks like this. Yeah, it's like a 1 in a circle. Well, it's because it is a 1 in a circle. It's a 1, which is an on, or a circle, which is off. That's why that symbol is in those switches. Yeah, I know. I wondered why that was for ages. Yeah, I thought the same thing. I wonder why is that a 1 or a 0? Well, it's reference to digital. Okay, high and low voltages. And our values for high voltages, while we're on this subject, is usually in digital electronics, which is where we use this. Okay, we use it in electronics. We use nice little voltages, and a high value, a 1 or a 0, is usually somewhere between 3.5 and 5 volts. And our low value, okay, that's our high value, and our low value is somewhere usually between 0 and 1.5 volts. Okay, so that would be 5 volts in a digital circuit. Yeah, the analog, well, it depends, whatever. You can have thousands of volts or whatever, guys. Okay, because what we're going to angle towards today is digital electronics. All right, so highs and lows, that's all it is, 1s and 0s. If the voltage is between that is a 1, is a 0. That's it. The middly bit, well, it doesn't work in the middle, guys. We just want highs and lows. All right, that's how electronics works. You will know this. You will know that computers are quintessentially stupid. Don't tell them I said that, all right? But guys, a computer is quintessentially stupid, isn't it? Okay, I mean, it can only count up to 1. A computer only goes 0, 1, 0, 1, 0, 1. It's not as smart as you guys. I know you yeah, okay. So it only counts 1s and 0s. But in its favor, a computer does that very, 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 very quickly. And therefore we can transmit all that data. The great thing about 1s and 0s is that they're very difficult to corrupt. Yeah, so if you want to copy things or send things, you can send very discrete packages of data, 1s and 0s, and it doesn't get distorted. Okay, and if it does, we can clean up the signal and make it nice and crisp again and ping through lots more 1s and 0s. Yeah, if it starts to get a bit wobbly, we can say, well, you know, that 3.7, it must have been a 5, and that 1.1 must have been a 0. Okay, and we can clean up the signals. So that's why copying things digitally is very easy and very reliable. Yeah, because it's just 1s and 0s. It's not all those other values. Well done, guys. Right, here we go. We've covered that. That'll do. Let's open the page. Let's throw this around somewhere. Digital electronics. Oh, that's the start. Come on, Mr. Monk. Chop, chop. Right. Okay, switches. Let's think about switches before we do electronics. All right. Now, as strange as it seems, we can put switches in parallel. No, we don't. Well, you can. Now think about your car. All right. Think about when you jump in a car. Yeah. Switches in parallel. If the driver's door is operated, the light comes on inside the car. If the passenger's door is operated, the light comes on in the car. The light can come on inside the car if you opened the driver's door, the passenger's door, or both doors. Yeah, because when the door opens, there's a little plunger switch which switches on the light. So we can get switches in parallel. All right, don't often talk about it, but today we are. Now, if the switches are off like this, we can say it's off, and Q is the light bulb. And we can say it's not working. Now, if we come along here and jump in the passenger's side, and that switch is operated, then that switch will close. Okay, B will close. The light will go on. Then, if someone gets in the driver's door, but this door is not operated, the switch goes, the light goes on. And if you open both the doors, the light is on. Okay? So this is a system where the output will come on if one or the other works. If one or the other works. So this type of switch, we could say, well, it's working if one or the other one works. We could call that an OR system. Yeah, that would be logical, wouldn't it? Now, switches could be put in series. Okay, so here they come in series, A and B. You say, we don't have switches in series, but we do, guys. Yeah, when you're in the car, if you try and operate the windscreen wipers won't work unless we have the car switched on. The ignition is switched on. So the windscreen wipers would only come on if you had the car switched on with the ignition switch and you operated the windscreen switch. Okay, so we haven't got windscreen wipers here because it's easier to draw a lamp. But if we had a lamp here or an alarm system, yeah, if you wanted to operate an alarm system, whatever it is, or open a vault or time or some kind of locking mechanism, and you wanted 2 codes put in, we would do this. So the lamp would only come on. If these are both open and not working, the lamp's not going to be on. If we operate just B, it's definitely not on. If we operate just A, it's not on. But if we operate A and B, it comes on. And this is called an AND system. Okay, right? Because it only works with one and the other. Now, look, you might be confused. You might say, well, that's an AND as well. all right? But just go along with the story. We call it an OR system. We call it an OR system. You can have something called an XOR, which we will be getting onto later. All right, we'll be getting onto XOR later. Did I put that on the things? Yeah, but back here, guys, on what to understand. We're going to look at gates, which are AND, OR, NOT, NAND, NOR, and XOR. Okay, so we are going to come on to that. But these are called an OR system and an AND system. Now, switches is one thing, but then we use something called gates. Okay, now it's not named after Bill Gates. All right, some people think it is, but it's not. Yeah, we get onto this thing called gates. And why do we use gates? Well, a gate is a miniature switch. All right, it acts like a miniature switch. Whether it's a switch or not doesn't matter, but it does behave like a switch. Okay, and what's the advantage of a gate? It's miniaturized because we like electronics to be small. We like it to be discrete. We like to be able to put little bits of electronics in all over the place. So a switch, which is a gate, it'll work on high and low signals like this. Okay, if it gets a 0 and 0 go in, nothing will come out and so on. Okay, it works on those voltages I told you about. It works on a digital signal. It works on a high voltage or a low voltage. Okay, it'll take in an analog system. It'll take in an analog signal, but it will come out as digital. Okay, it will only come out as a high or a low. Gates are very reliable. They last a long time. They are very, very, very quick. So they're great for gaming and this type of thing. Okay, and also there's no moving parts, so they don't wear out very easily. So they're small, they're quick, they're reliable, they last a long time, and some of them are very cheap to make. Very, very cheap to make. All right. So what we do is in electronics, where we want to switch, we replace it with a gate. Okay, we replace it with a gate. Right. So what we do is we have these things called gates. Now I've covered a lot of them up. Okay, and there's a reason for that, and that is that there's so many of them to look at. All right. So we've covered a lot of them up, but this is it. This is where we're going to learn our little bit of digital electronics today. Okay, so, all right, with an AND gate, it has two signals going in and it's got one coming out. So A and B are the signals going in and Q is the output. All right, so instead of having switches that we physically switch on and off, it just has a signal going in and it's otherwise off, or one is on, or they're both on. Okay, so this is an AND gate. All right, now you know what's going to happen. The clue is in the name. Well, from here, it only comes on when one and the other are on. So Q stays off for all of those times. I think that's pretty cool. Here comes our OR system. Okay, so in our OR system, what we have is we've got A and B go in. So same thing, they can be 0, 1, 2, or 3. That's binary. That's binary for 1, 2, 3. Okay, so there's 4 different states. And if it's an OR system, and that should be like a little shield, but it's a bit wibbly, guys. An OR system would give us this. Yeah, this would be like the switches in parallel. This is like the switches in series. Okay, so if you've got 2 signals which go in and you want it to come on for either of them, then that would work. Okay, all right. So that's that type of switch. Guys, this can be used in loads of different places. But this one here, an OR system, could be used in a greenhouse. If you've got a greenhouse and you want it to be watered at nighttime or when it's dry, you can have B is the nighttime switch and A is the dry switch. Okay, and then when it's dry, you get a 1 signal, the pump switches on. When it's nighttime, the pump switches on, and when it's nighttime and dry, the pump switches on, and you can irrigate your greenhouse. That could be it. Simple, or it could be some type of alarm. Okay, next we get a NOT. Now, I love these this bit of physics, guys, because it tells us what's going on. They haven't called it something obscure like a fandango gate. Yeah, it tells us what it does. And a NOT gate, whatever goes in does not come out. It's just got one input, one output. So if a naught goes in, one goes out. And if a one goes in, naught comes out. Okay? So we have a NOT gate. Now, what we sometimes do, we want to reverse these signals. You know, electronics is very complex, and we want to reverse these signals. And when we do, we combine the gates, and we end up with an AND gate, which operates quite differently. So we can have an AND gate, which we put through a NOT gate. See there? No circle. There's the circle. So a NAND is an AND and a NOT. And because we like taking shortcuts in physics, instead of calling it a NOT AND gate, we call it a NAND gate. So it's the opposite to an AND. So that would be 1, 1, 1, 0. It's the opposite to the AND. You've got it. Along comes the NOR gate, and the NOR gate is opposite to the OR. So it's 1, 0, 0, 0. And because I've mentioned it earlier, but it's not on your syllabus if you're doing the Cambridge course, but you might as well know about it, guys. You can get an XOR gate, which is exclusively OR. All right? An exclusively OR gate would give us, it doesn't work for the AND, it only works for OR, right? Because some of you guys would have spotted that previously, right? Now there's lots here, but the good news is this: these names relate to what they do. And this is a NOT AND, and that's the NOT OR, and that's the XOR. So logically, we should be able to get our heads around this pretty quickly. Yeah, the symbols, that's like a D shape, and that's a shield, and that's like a diode, but it's got a circle on the end, and then that's like that with a circle, and that's like that with a circle, and that's the XOR with the extra piece on it. Okay, and the way I remember it is this. Okay, I just remember two things. I remember the NOT. It's not quite a diode, right? That's easy to remember. That's not quite a diode. And the AND gate, no. If I write down the word AND, A-N, there's the gate. There's the gate there, guys. It's the D in AND. Once I've remembered that, everything else makes sense, because I know what the other one is, that shieldy thing, which looks a little bit like that. That's a terrible drawing. Okay. Thank you. That's much better. You're welcome. Okay. So that'd be our OR gate. I only remember the AND. And the NOT, okay, well, you know, it's not a diode. It almost is, but it's not. See, just remember that, guys. All right. Truth table is nice and easy. It's just binary. 0, 1, 2, 3. Yeah. Okay. Well done. Well done, guys. Okay, we're moving on. It is quite tricky. And we've done all this. We filled this one up, guys. So what we need to do is to start a new one. And our new one is ready to go. It's here. Now look, it's quite tricky. So let's have a quick look at this now. Okay. Let's look at this one. This is the last couple of things we're doing now. So we're going to add the gates together. When we add the gates together, we've got A and B as the inputs. They form C. C goes through another gate and it gets out of Q. Okay. Now, what type of gate is that? Well, it's the D, isn't it? So we know it's an AND gate. So we know that C is going to be high when A and B are high. So this is 0, 0, 0, 1. But then it goes through a NOT gate. So whatever goes in does not come out. Ka-ching. So this construction is actually a NAND gate. That's how we make an AND gate. Got it? All right. Now, it gets ugly, guys. All right. But this is a pretty ugly as it gets, okay? We have 3 inputs, okay? We can have 3 inputs. So when we have our 3 inputs, then what we end up with is A, B, C are our 3 inputs. So it can be, it's just binary counting, 0, 1, 2, 3, 4, 5. Have I missed one out, guys? Let's try that again. I don't think I have. 1, 2, 3, 4, 5, 6, 7. Okay, so that looks all good to me. So I haven't missed one out. There should be 8 of these altogether. Look, 1, 2, 3, 4, 5, 6, 7, 8. Just check, right? You can see that I made a mistake earlier. Look, guys, and I've had to glue a little bit of card on here because I missed one out. Yeah, I'm just jotting things down merrily. All right, now we've made a little correction here with a lovely bit of cardboard, which some of you didn't spot. Thank you for not spotting that, guys. All right, now what type of gate is this? Well, even with my wibbly diagram, you can see that it's a NOR gate. Okay, a NOR gate. If it was OR, it would be 0, 1, 1, 1. But in fact, it's going to be, the output's going to be 1, 0, 0, 0. So with a NOR gate, yeah, A and B are going to give us output D. So we look at A and B, we ignore C, and we look at D. A and B go through to D, okay? And it's going through a NOR gate. So we could just write that truth table down, or at least think about it, okay? But we do know that it's only a 0 and 0 will give us a 1. So ignore the C, 0 and 0, D gives us a 1. 0 and 0 gives us a 1. That'll give us a 0. That'll give us a 0, and that will, and that will, and that, and that. Okay? Now this is a NOT gate. Whatever goes in does not come out, and that goes to E. So C goes to E. So that would be 1, 0, 1, 0, 1, 0, 1, 0. Okay? Now, D and E, that looks like a D for AND, but it's got a circle on the end. So it's a NAND gate. And so for a NAND, it's opposite to an AND. So a NAND would be a 0 if we get 1 and 1. Okay? So 1 and 1 would give us a 0 because it's a NAND gate. Okay? NAND gate, 1 and 1 give us a 0. Everything else gives us a 1. Okay? 1 and 1, D and E, give us a 0. Look at all these. All right? These are all going to be 1s. That's it. Job done. Okay? All right, guys. So that's about as tricky as it gets. You could get something like this. You could get a circuit with 4 inputs, okay? But you'd have to count up in binary from 0 to 1, 2, 3, 4, 5, 6, and right the way through, okay? So that would be a very, very long column of numbers, all right? There's some sample codes there. What type of gates are these? These are AND gates. Both of these are ANDs. A and B gives us E, okay? So it's an AND system. A and B will give us 0, 0, 0, 1. C and D go to F. That will give us an AND system, 0, 0, 0, 1. And this gate here is an OR gate. So this would be high if one or the other is high. That's it, just from those sample codes. Okay, now we haven't got time to fill this all in, but you would have to count from here, from binary, and then go 1, 2, 3, 4, and so on, all the way down till you've got 4 1s at the bottom. Yeah. Do you know, guys, for IG, nothing gets worse than that. If you can nail this, just sketch them out and try them yourselves. Nothing usually gets any worse than that, guys. All right. Here's something for you. Some of you will be saying, hey, hold on, what about a NOT gate? How can you have a gate where a 0 goes in and a 1 comes out? Yeah, that's impossible. You can't create a voltage. I don't know. Well spotted, you guys. We power up all the gates. All the gates have power going into them. They have a power supply. Now, all of them do. They all have a power supply, which is separate to the input signal. The power supply is separate. Okay, now they all have a power supply. So we don't bother drawing it on because it's going to get complicated. All right, so well spotted, you guys. If you go, whoa, how do you get a 1 when there's only a 0 going in? We have a little old power supply to make the gates function. Okay, so well done. Right, I think we have covered most things there. All right, we have done a lot. Yeah, so well done, you guys. Let's go back to our introduction sheet. Have we? Yes, we have. We've understood analog and digital signals. We've looked at gates. All of these. XOR is not on the Cambridge syllabus, but some of you guys might not be doing Cambridge, and it might be there. And it doesn't do any harm to learn a little bit extra. And the truth tables. Okay, guys, you have done really well today. All right, if you've understood that, you have done so well. Right, well, we're just about finished, and I will see you next time. Thank you and goodbye.